Before I get on to how we solve our current problem, I think it's a bit easier for me to explain how to solve a similar problem where there's less number of components. So as you know, we've got M and N and they're 50 components big. It's a bit hard to see what's going on with 50 components. So I'd rather just do another smaller example and show how the concept of that smaller example makes sense for our problem of 50 components. So what I mean by that is we want to multiply the molecular weight, the molar mass of each component in our vector of M with each element in our vector for molar flow rate 18, 17 and 23. So we want to multiply the first element in M with the first element in N. We want to multiply the second element in M with the second element in N, and so on and so on. So to see this, let's make just two smaller vectors. I'm going to call it MM, just to make it different from the current M that we have. And let's say we just have a 3-component stream, and the molecular weights of these 3 components are, let's say, 10, 20, 30. Okay, and it happens to be a row vector. Doesn't matter, we could transpose it if we really wanted to. But point is, we've got 3 components for a 3-component stream, and the molecular weights are 10, 20, 30 grams per mole, let's say. Then we've got the molar flow rate, so I'm going to write another variable, NN. Remember, this is just for a hypothetical 3-component stream. Let's say that the molar flow rates are 0.25 and 0.75 and 0.38. Okay, I've got the molar flow rates of 0.25, 0.75, 0.38. And now, what would be the mass flow rate of the first component? Well, if the molar flow rate of the first component of our hypothetical 3-component stream is 0.25 and our molar mass is 10, then it would be 0.25 times 10, 2.5. Okay, but how do we write that in terms of the variables M and N? So I'm just doing this all in the command window to make it a bit easier to explain. But the point is I could write MM, and how do I access the first element inside this vector? Well, it's the first element, so I know I must use the round brackets, and it's number 1. MM, curly brackets 1, gives me 10, which is the first element inside this vector MM. If I wanted to the second, I could write 2. If I wanted the third, I could write 3. And they would give me the corresponding molecular weights for this MM vector. So let me just clear things to make it a bit easier. So I've got MM and I've got NN. And so if I wanted to find the mass flow rate of the first element, well, it's MM, the first element of MM, times, well, the first element of NN, the molar flow rate. And you agree that that's the same as me writing 10 times 0.25. If I wanted the second, it would just be MM of 2 times NN of 2. And that's 15, because indeed 0.75 times 20 is 15. 0.75 times 20. Let's just prove it to ourselves. Is 15. Yes, it is. And if I wanted the third, mass flow rate in this hypothetical 3-component stream, then it would be the third molar flow rate times the third molar mass, and it's 11.4, which makes sense because it's 0.38 times 30. So that's the idea. That's what we want to do now, but we don't have 3 components in our stream. We've got 50. We've got 50 components in our stream. But can you see that the way that we do this problem is the same as how we should be approaching this problem with 50 components. Instead of doing this 3 times, we want to do this 50 times. We want to do the same multiplication 50 times. So that's why we'd want to want to create a for loop. So that's what I'm going to do now. The first thing I'm going to do is I'm going to make a vector to hold the answers of my mass flow rate. So let me call it M. Small m represents the mass flow rate of the components in my 50 component stream, and I'm going to write, it's going to be a variable, and let's make space for 50 components. So let me write zeros. Zeros is a function where I can make a matrix just full of zeros, and it's going to be 50 by 1. Actually, let me make this a bit simpler. Let me clear it up a bit more by saying let's make a variable called number of components equals 50, and then I can put the number of components here, and you'll see why that's useful later on. So I've made a variable called number of components to designate the number of components in my stream, which happens to be 50. Then I've made a variable called m, small m, that represents the mass flow rate. And now what I want to do is just repeat what I've done here for this 3-component system, but now for 50 components. So the way that I can do that is by creating a for loop. So I'm going to write for I equals 1 to 50. But instead of writing 50, I've created a variable called number of components. So let me write number of components there. This makes it easier for me to read later on what's happening. I know that this is the number of components. Then what's going to happen inside this for loop? Well, I'm going to have to multiply 50 molar masses. So I'm going to start at I equals 1, and I'm going to multiply the first row of capital M with the first row of small n. Then I'm going to loop again, and I'm going to multiply the second row of capital M with the second row of n, small n, and so on, up until 50, number of components. So what I really am trying to write is m of I times n of I. Right? This multiplication says take the ith element of capital M and multiply it by the ith element of small n. And what is I? I is 1 in the first iteration. Then this loop goes around and I becomes 2. So this becomes m brackets 2 in the second iteration. Then it loops around again. I becomes 3. This becomes m brackets 3 times n brackets 3, and so on and so on. So can you see, by me placing I in these curly brackets, what I'm doing is I'm accessing each element one by one and multiplying them together. So what is this number? This is a product. It's a scalar number, and I want to store that number somewhere. So I'm going to store that in the ith element of the vector that I created to hold the mass flow rates. So I've created a vector. It happens to be a 50 by 1 column vector, and it currently contains zeros at this point at line 106. When I go into the loop, I start to fill in the numbers in this matrix. So I replace all the zeros with the actual mass flow rates. So the ith element in this mass flow rate vector is equal to the product of the molecular weight for the ith component times the molar flow rate of the ith component. And let me type in there, and I don't want everything to spit out to the screen, so I'm going to put a semicolon there. And actually, let me write here at the top clear and CLC. Clear just clears all the current variables when I run this program, and CLC will clear the command window. Okay, so let me save that again. Save. And if I run it, let me run. The code executes, and now I have, if I look at my workspace, there's a whole bunch of different variables that have been created. I've created big M, small n, small m, number of components in I. All of these are variables that I've created at some point in my script. But what's nice is this for loop has gone and worked out for me all of the mass flow rates for my 50 component stream, and I can look at that by going into the command window, typing M, and you'll see that I've calculated all of the mass flow rates for all 50 components in my screen with just 3 lines of code. Just 3 lines of code. I've done a huge amount of work, and that's why for loops are great. So the next video I'm going to finish off this script and show how we can work out the mass fractions and the mole fractions for this 50 components stream.